In the last lecture, we looked at combination of a reflection operation and a translation operation. We will begin this lecture now by looking at what happens or what kind of a symmetry operation we get if we combine a rotation axis with a translation. So, combination of rotation and translation. So, let us say that and this also still we are discussing in 2 dimensions. So, I have a rotation at point A through an angle of alpha, and along with this I also have a translation. Let me say this is my x and y. So, what I am looking at is I first rotate, follow this up with translation, and what is the resulting operation. Now, we will first do this with using matrices. So, we know the matrix for translation T that we developed last time. So, for a translation of T, the matrix in homogeneous coordinates 1 0 T 0 1 0 0 0 1, and we have used the rotation matrix very often, and that is simply cos alpha minus sin alpha 0, sin alpha cos alpha 0 0 0 1. Now, we multiply these 2 matrices, very simple. What one would get would be cos alpha minus sin alpha T, sin alpha cos alpha 0 0 0 1. Now, this resulting matrix we have to now figure out what kind of a operation is this. So, let us look at another matrix that we have already derived earlier, and that matrix was for that there is a rotation not at the origin, but at a location given by the coordinates a comma b. So, let me call this as, let us say, point B, and we will look at it that if there is a rotation of alpha there, then B alpha, we had derived this earlier in an earlier lecture, cos alpha minus sin alpha, then I have A times 1 minus cos alpha plus B sin alpha, sin alpha cos alpha I have minus A sin alpha plus B times 1 minus cos alpha, and then I have 0 0 1. Let us compare these 2 matrices. The matrix B alpha simply describes the rotation about a point of coordinates a comma b through an angle of alpha. So, if you look at it, we compare element by element. So, the first 2 elements of the first row, first 2 elements of the second row, they are identical. Last row is of course identical. So, the only elements that we are interested in is the third element of first row and second row. If let us say that This looks like what we have got as a result of the combination. This looks like some kind of a rotation. If it is, and if it is, and it looks like it's a rotation of alpha only, we compare to equate the two elements. Equate the first element of both matrices in the first row. Same way you equate the third element in the two matrices of the first row should be equal. Third element of the second row in both the matrices should be equal. So, let us try to do this, which basically means, so I look at this element and compare it with this, and I write down the equation A 1 minus cos alpha plus B sin alpha should be equal to T. Similarly, now you look at this element and equate it to the element which is 0, minus A sin alpha plus B 1 minus cos alpha equals 0. Now, let us say this is my equation 1, this is equation 2. Let us eliminate B in these two equations. So, what we do? We divide 1 by sin alpha and 2 by 1 minus cos alpha, and then subtract the two equations. So, if we do this, the result would be A times 1 minus cos alpha upon sin alpha plus sin alpha upon 1 minus cos alpha, and this would be equal to T divided by sin alpha. Now, what we can do? We can do further with this equation. Let us rearrange things. So, I can write A upon sin alpha 1 minus cos alpha, and I will have out here 1 minus cos alpha square plus sin square alpha equals T divided by sin alpha. Now, at this stage I can cross out these sin alpha and expand the 1 minus cos alpha square. So, what I will get when I expand 1 minus cos alpha square? I will get 1 minus 2 cos alpha plus cos square alpha. Now, if you look at that equation, cos square alpha plus cos square alpha you will get, we will add it up to sin square alpha, that would give me equal to 1. So, the final result that I will get would be A, in fact, I will get 2A times 1 minus cos alpha, and then I have in the denominator already 1 minus cos alpha, which is equal to T. So, now 1 minus cos alpha will cancel out, giving me A to be equal to T divided by 2. So, I have got one coordinate now of this rotation axis that we expect, that A is half the magnitude of the translation. So, therefore, we are looking somewhere here. Now, we have to find the B coordinate that will tell me how far we have to go away from the translation. Now, to find B, I will substitute A equals T by 2 in equation 1. So, if I do this, I will get t upon 2 times 1 minus cos alpha plus b sin alpha equals t. If we take leave b sin alpha on one side, so b sin alpha equals t minus t by 2 times 1 minus cos alpha, and this becomes t by 2 into 1 plus cos alpha. Therefore, b becomes t upon 2 1 plus cos alpha divided by sin alpha. Now, further we can rewrite this 1 plus, and instead of writing cos alpha, I can write this as cos square alpha minus sin cos square alpha by 2 minus sin square alpha by 2 divided by same thing here 2 sin alpha by 2 cos alpha by 2. So, very clearly the numerator, we can write the numerator now 1 minus sin square alpha by 2 is cos square alpha by 2. So, we can write this as 2 cos square alpha by 2 divided by 2 sin alpha by 2 cos alpha by 2. So, this will become t by 2, this 2 will cancel, cos will cancel. So, I am left with t by 2 into cos alpha by 2 divided by sin alpha by 2, and that is nothing but t by 2 times cot alpha by 2. So, now I have got both the coordinates a and b. So, therefore, where should the second rotation axis lie? So, I expect that if I started out with a alpha with a translation t. So, a coordinate is t by 2. So, we are right at the midpoint of this, and then one can go up. So, this is the coordinate t by 2, and this length should be t by 2 cot alpha by 2. So, this is where I expect another rotation axis which rotates through an angle of alpha. Now, what I will do is that it is quite instructive if we look at the same process through and give a geometrical proof of this. That will give a much better feeling for what is happening in the two-dimensional plane. So, let us see how the geometric proof looks like. In fact, geometric proof is quite simple. So, let us say I have the rotation axis as point A, a translation of vector t, and very clearly if I do some rotation, then things will rotate in space, but what we will do is we will do a clever construction, and the construction that I will do is let us take a perpendicular to the translation direction and draw a line at an angle of alpha by 2, and let me call this as line 1. Now, I rotate this line through an angle of alpha, the required rotation at point A. So, when I do this, this line will rotate to a new position, and let me call this as line 2, and very clearly this angle has to be alpha by 2. Out here this angle is also alpha by 2. Now let us translate. So, I have done the rotation, now I have to follow it up with translation. So, let us translate the line 2 through the translation T. If I do this, this entire line will translate and come to another position, and I will call that as line 3. Now, suppose there was a point that we keep track of. So, there was a point. So, there is a point, let me call that as point P1. This point P1 will also rotate as the line rotates, and it will come to a new position, call it as P2. And when we translate, this point P2 will come to a position on line 3, and I will call that as point P3. So, what I am trying to say here is that point P1 goes to point P2 when we give a rotation of A alpha, and P2 goes to point P3 because of the translation T. So, essentially we are trying to look at that how can we go from P1 to P3. Now, in this I will invoke one property of the point symmetry, and that was that there would at least be one point that would remain invariant after the point symmetry operation. So, if it is a rotation axis, it will be a point on the line axis itself. If it is a reflection operation, then the points on the mirror plane would be invariant. Now, let us see, is there an invariant point in this diagram? Let me label this point as C. When we rotated the line 1 through alpha, this point C would also have moved to C prime, but the translation would bring it back. So, after doing a rotation operation followed by a translation operation, the C point remained where it was, which means that our rotation axis would also be located at point C. So, this becomes my where the rotation axis would be. And we can see from this diagram, one of the things that we can note out here, that if I drop a perpendicular onto the translation line, we can clearly see that this is going to bisect the translation. So, in fact, this would be T by 2, this length would be T by 2. So, this is a perpendicular bisector of T. So, very clearly our rotation is lying on the perpendicular bisector. So, this becomes one of my coordinates now, T by 2. The second coordinate is vertically up. So, we have to find out what is this length. Well, this length very clearly, if you look at it, this angle is alpha by 2, this angle is also alpha by 2, this angle is also alpha by 2. And therefore, this point C is located on the perpendicular bisector at a distance of T by 2 cot alpha by 2. So, I have found out my rotation operation. So, let me call this as C alpha now. That C alpha, it is located at T by 2 comma T by 2 cot alpha by 2. This is exactly the same result that we had got through the matrix multiplication. So, now what else can we do? So, I have this expression. What we can do is, what would happen if I had a two-fold rotation axis and a translation, or if I had a 3-fold rotation axis and a translation, or a 4-fold and a translation, or a 6-fold. So, these various combinations. Well, 2-fold and a translation, alpha is equal to pi, rotation of 180 degrees, which means that T by 2 cot alpha by 2, then this value clearly it will be a cot of pi by 2 and which is 0. 3-fold alpha is equal to 2 pi by 3. What we will get would be T divided by 2 root 3. Alpha in 4-fold is pi by 2. So, I am looking at cot of 45 degrees, and that is simply T by 2, cot of 45 degrees is 1. Finally, hexagonal case, hexagonal rotation or a 6-fold rotation, alpha is equal to pi by 3. So, cot of alpha by 2, which means it is cot of 30 degrees, and that is simply what we will get would be root 3 upon 2 times T. So, now what does this mean? So, when it is a 2-fold, so I have a 2-fold and a translation. The coordinates of the second 2-fold should be on the translation vector itself at the midpoint. So, this is the second 2-fold that gets generated. In the case of 3-fold and a translation, I will get a 3-fold, but it is at a certain distance from here. In fact, I will get it up, I will get it down as well. If I do a rotation of minus alpha, similarly, so this length would be T upon 2 root 3. Now, the third case, we are looking at 4-fold and a translation. Now, in this case, it is going to be again on the perpendicular bisector, and another 4-fold will show up here, and another 4-fold likewise will also show up out here, and this would be at a distance of T by 2. And finally, 6-fold, again on the perpendicular bisector, I will get another 6-fold, and this would be root 3 by 2 times T. So, we have now combined rotation with translation, and we have shown what should be the new rotation axis, where it should be through both matrix method as well as a geometric method. With this, I will close this lecture.